So today for Math 3, we're going to start our last unit. And this is the first topic of the last unit. We're looking at exponential graphs. Okay, so we have a basic exponential function. And it looks like this. F of x equals b to the x. And whatever the b value is determines whether it's a growth or decay function. So let's look at what growth and decay look like. Okay, if you have an equation where you have f of x and you want your b value to be greater than 1. Okay, so you have some examples. You can do 2 to the x, 5 to the x, 100 to the x. As long as the b value is bigger than 1, all right, then you will have a growth function. So it will go up, like this. Then how steep the curve is dependent on the number that you have as your b value. Okay. The bigger the number for b, the steeper the curve is going to be. Okay. For a decay function, it's the same format, but b is going to be greater than 1. Sorry, it's going to be greater than 0, but less than 1. All right, so it has to be, basically, you're thinking about this as a fraction or a decimal. Okay, that's less than 1, but greater than 0. So you could have 1/2 to the x. All right, 0.25 to the x. Okay, something like that. So those are both fractions or decimals that are greater than 0, but less than 1. All right, and for these, they're going to be going down. They're decaying. And how fast they're decaying is dependent on the b value. Okay, so let's look at some of these examples that we have here of exponential graphs. So you should be able to identify the graphs just by looking at them. Okay, for the first one, we have f of x equals 4 to the x. Because the b value here is bigger than 1, this is a growth. Oops, spelling would be good. I'm just going to put G to make it easier and consistent. Okay, here we have f of x equals 2/3 to the x. Now 2/3 is bigger than 0, but it's less than 1, so this is a decay. Here we have 1/4 to the x. Again, bigger than 0, but less than 1. This is a decay. Now here's a tricky one. 3/2. This is a fraction, but 3/2 is bigger than 1. So although it's a fraction, it's still a number that's greater than 1. So this is a growth function. Okay, to be a decay function, you have to be between 0 and 1. Can't be bigger than 1 to be a decay function. So let's look at some of these things and what their values look like when you're doing these problems. So let's start with our growth function. We have 4 to the x. So if we put in -1 for the x value, we're going to get 1/4. If we put 0 in for the x value, we get 1. 4 to the 0 is 1. Actually, anything to the 0 power is 1. And then 4 to the first is 4. So your graph should look something like this. It's getting bigger. It's a growth function. Okay, let's look at our first decay function. We have 2/3 to the x. All right, so 2 divided by 3 to the -1 power gives you 3/2. So 1.5. 2 to the third to the 0 gives you 1. And 2 to the third to the first power gives you 2/3. So this graph will look something like this. It's decaying, it's going down. Okay. Try the next one. Now we have another growth function here. So remember we had 3/2 to the x. Okay. If we have -1, so 3/2 to the -1 power gives you 2/3. 3/2 to the 0 power gives you 1. And 3/2 to the first power gives you 3/2. So it's again getting bigger as we go along the x-axis. Now this one won't be as big as the 4 to the x power because the number for b is a smaller number, so it won't get as big as fast. It'll still get big fast, but not as fast as the 4 to the x. Alright, and the last one we had was 1 to the 4th. Or sorry, 1 over 4 to the x. So, 1/4 to the negative 1 power gives you 4. 1/4 to the 0 power gives you 1. 1/4 to the first power gives you 1/4. So we have something that looks a little bit like this as a sketch. All right, so those are some examples of our growth and decay functions. Notice growth, as we go from left to right, is going up. Decay, going left to right, is going down. So let's look at some examples of, or sorry, some characteristics of these graphs. Okay. So, a basic exponential growth function, the sketch of the graph we just looked at 2 examples, is going to look like this. It's going to be going up. Whereas a basic exponential decay function is going to be going down. Put arrows on everything. Okay. Your domain. Domain is talking about what values exist for your graph on the x-axis. So if we look at our graphs, there's no asymptotes, there's no holes or anything. There's nothing that's getting in the way of it going from negative infinity, oops, that was ugly, to positive infinity. And the same thing goes for a decay function. For the range, now this is a little more tricky. You would think that the graph is going up for a growth function, that it's going up from something, and it's going up from the negative, but that's not true. Okay? In a basic exponential growth function, it's not going to cross the x-axis, so it's never going to get to 0 on the y-axis. So what we say is it can go really close to 0, but it can't actually touch it, so that's going to be 0 with a parentheses, because it's not actually going to include 0, going up to positive infinity, because it's going up. Okay, the same thing goes for a decay function. Although it's going down, it'll never actually touch the x-axis. And now you think it's going from positive infinity to 0, because that's the way it's going as the graph goes. Okay, we still write our range as 0 to infinity. So we go from the lower number to the higher number on the y-axis. Okay. Now these might change, especially not so much the domain, but the range might change, all right, depending if you have any transformations to your graph. So if it goes vertically up or vertically down based on a value being added or subtracted on the outside of the function, that range might change because the graph might vertically shift up or down. Okay. Asymptotes. Well, we just talked about this with the range value. Our graphs for both growth and decay are never going to actually touch the x-axis, which is technically it makes it like an asymptote. It'll get really, really close to the x-axis, but it won't actually touch it. So we use that x-axis as an asymptote. So that's going to be y equals 0. Okay, so you think about it, y equals 0 is a horizontal line on the x-axis. It's kind of like a barrier that the graph won't cross. All right, x-intercept. Well, we talked about this too. Since the graph's never going to cross the x-axis, there is no x-intercept. Now again, this might change depending on if you have a vertical shift. If you shift the graph down like 2 spots, all right, because you have -2 on the outside of your function, the whole graph's going to go down, which means eventually the graph will cross the x-axis because you shifted the whole graph downwards. All right. So the y-intercept, where the graph crosses the y-axis, if we kind of go back up to our table of values up here for all these functions, all right, we see that there's a consistent y-intercept. Every time that x is 0, y is always the same number. Okay, so your y-intercept is going to be 1 for both of these functions. Again, depending on shifts, either horizontal or vertical for that matter, your y-intercept might change. Okay. Excuse me. Okay. Intervals of increase or decrease. So between what intervals is the graph increasing or decreasing? So a growth function is going to be increasing over the entire domain. So the whole time the graph is going up. Okay. Versus the decay function, the whole time it is decreasing. Now, end behavior for this particular function is a little bit different. Okay. Excuse me. All right. So the end behavior for this. So as x is approaching negative infinity, what is the graph doing? So let's go up to our graph. As x goes to the left, what is the y value doing? So it's going closer and closer, not to infinity, but to 0. It's getting close to 0, but it'll never actually get there. Okay, so it's going down, but it won't go down towards negative infinity because it's being stopped by the x-axis and that asymptote that we've put on it. As x goes to the right towards positive infinity, what is the graph doing? So let's go back up to our sketch. As we go to the right on our graph for our growth function, the graph keeps going up. So the graph will be going up towards positive infinity. Oops. Let's make that nicer. Okay, there's no restrictions on how it's going up. Okay. And behavior for a decay function. As x is approaching negative infinity, what is the graph doing? So over here, as the graph goes to the left, what is the graph doing? It's going up. So it's going towards positive infinity. But as the graph goes to the right, towards positive infinity, let's look at the graph again. As the graph's going to the right, it's going towards 0, but it's not going over 0. So f of x will be approaching 0. It's never going to actually touch 0, but it's going to get close. So let's try some examples here and do a couple problems, and then we'll try some practice problems. All right, the given functions are sketched on the coordinate plane below. Okay, we want to label each function. So there's 1, 2, 3, 4, 5 functions. So we're missing one, but that's okay. All right, notice they all have an x-axis, or sorry, a y-intercept at 1. So we talked about that before, up at the table up top. All right, so the first one, we have f of x equals 2 to the x. So we want to know which function of this is going to be, which line is going to be 2 to the x. So we're looking for one of the growth functions, so it's going to be 1, 2, or 3. Those are the ones that are going up. We can find out the right one because we're looking at if 2 to the first power, so if x is 1, it'll be 2, so it's going to be right there. So this graph right in the middle is 2 to the x. Okay, next we have 3 to the x. So at 1, where's the graph going to be 3? This one, so that's 3 to the x. Notice, because the b value is bigger, it's going to be a steeper graph going up than the 2 to the x. Next we have j of x to the 3/5. Right? Because our b value is less than 1 but greater than 0, this is a decay function. Well, there's only one decay function. It's this one over here. And lastly, 1.3 to the x is going to be this one by process of elimination. Oops, by process of elimination. Okay. But also makes sense because 1.3 is about right there on our graph. This is 1.3. All right, so for part B, it says consider the function m of x equals e to the x. Use your knowledge of the approximate value of e to sketch and label its graph on the coordinate plane to the right. Okay, I'm going to erase some of the stuff I've drawn on this graph just to make it easier to look at. Okay, so e is actually a number. Think of like pi. Pi represents 3.14 and a bunch of other things after it. E is also a mathematical number. So if you look on a calculator and look for like a little e that looks just like the one you see on your problem for part B, E represents 2.718 and a bunch of other things, kind of like pi does. All right. So if we have e to the x, we're looking for where is that going to go on our function. So it's 2.7, okay, approximately. So that means it's bigger than 1, so it's going to be a growth function. So it's going to start off low and go high. So we can make a graph that does something like here, goes through 1, but then it's got to hit 2.7 about there for where x is 1. So it's going to be a point that's somewhere around here. So as we go through 1, we're going to go through this point, and it's going to go in between 3 and 2 to the x. Okay? And that's what e to the x would be. Okay. For part C, using the functions f of x equals 2 to the x, and then 3 to the x, and then e to the x, what are the values for each one of those functions where the x value is 2? So all you're doing here is you're putting, oops, sorry, that wasn't supposed to happen. Okay, you're putting 2's in for the x values. So you have 2 to the second, which would be 4, 3 to the second, which would be 9, and e, let's figure out what e to the second would be. Would be 7, oops, I wrote a 4, silly, 7.39. Okay, so you're just valuing or finding the values where x is 2. So you're just raising each of those values to the second power and figuring out what it was. Now for e, you'd have to use your calculator because, well, it makes the most sense. All right, last question. Yep, last question is an example. So we have our function f of x equals 1/5 to the x power. Because 1/5 is a number for b that is greater than 0 but less than 1, this is a decay function. Okay, so we can sketch a graph. I'm going to put 1 right there with a point, and our graph's going to look something like this as a sketch. Okay. All right, let's go through some of the things here. For your domain, for the x terms that exist in this graph, well, it's all of them. So negative infinity to positive infinity. For the range, the y values that exist in this graph, well, it doesn't go below the x-axis, so we're going to go from 0 to positive infinity. It just goes up. Notice that the 0 is not a bracket because it doesn't touch the x-axis. It gets close to it, but doesn't actually include it. Your asymptotes are going to be that x-axis that you can't cross. It's y equals 0. Your intercepts. So you only have one because there's no x-intercept. There's only a y-intercept. And it is at 0, 1. Your end behavior. So as you're going left on your graph, as x approaches negative infinity, your graph is going up. As it goes to the left, it goes up. So what are we calling this graph? f of x. Okay, just making sure. It's going up towards positive infinity. As the x goes to the right towards positive infinity, what is the graph doing? As it goes right, it goes down, but it's only going down towards 0. So it's approaching 0. And then is it an interval of increase or decrease? Well, the whole graph is going down, so it's decreasing over the entire domain. And that's it. All right. Please try the practice so we have something to talk about on Wednesday, and good luck. If you want to do test corrections, they're up online. You can do those as well.